Welcome. I wanted to tell you about dielectrics and capacitors. And so a dielectric is, we're going to say that a dielectric and a capacitor is a non-conducting material, like in other words, an insulator, that when placed between the plates of a capacitor, it changes its capacitance. So most capacitors will have dielectrics in them, and that's because they offer three basic benefits. Here are the three basic benefits to putting a dielectric and a capacitor. One is the dielectric is might be like wax or mylar, and so when you put it in between the plates of a capacitor, it helps hold the plates apart, because we don't want the plates of a capacitor to touch because it will short out. So it's much easier to prevent the plates from touching and get them really close but not touching if you put a material between them. Then they're less apt to short out. The second thing is the dielectric. I'm going to explain this a little more in this video, but I'm just going to read it to you now. The dielectric increases the maximum potential difference between the plates before the capacitance starts to conduct. So you can put more charge on a capacitor before there's only so much charge you can put on a capacitor before it will let the charge go from one plate to the other. And so this, by putting in a dielectric between them, it allows you to put a little more charge, sometimes a lot more charge, on the capacitor before it shorts out. And then the big one for this unit is going to be that dielectrics increase the capacitance of a capacitor. So if you put a dielectric in, you might double the capacitance of a capacitor or triple the capacitance of a capacitor. Okay, so we're going to start out with this one. That's all I'm going to say about number one. Number two is at the end of this video or in another video. Okay, so let's talk about how it increases the capacitance of a capacitor. All right, so look at this table. So if you don't put anything in a capacitor, and you don't even put air in between the plates of a capacitor, then it's going to have a certain capacitance, and as soon as you put in air or Teflon or Mylar or glycerin, you're going to increase the capacitance. Now, if you put air in, you only increase it by 1.00059 times. That's at 1 atmosphere. So, but if you put Teflon between the plates, you increase it 2.1 times. If you put Mylar in between the plates of a capacitor, you increase the capacitance by 3.1 times. Glycerin or glycerol, you put that in, and it's going to be 42.5 times approximately. So that's called the dielectric constant. The dielectric constant, that you might think that's a K right there, but that's really a kappa. But anyways, that dielectric constant tells you how much it multiplies the dielectric or the capacitance by. So the vacuum, if the vacuum is 1, and anything else that's an insulator increases it from a vacuum. Again, we'll talk about this dielectric strength in a little bit. The dielectric strength has to do with how much charge you can put on before the capacitor starts to short out. Okay, so what I'm saying there is, if you know the dielectric constants for a material, then this will tell you to get that dielectric constant, it's just going to be how much capacitance is when you have it in there, divided by when you don't have it in there. So the capacitance with the dielectric is C, and then the capacitance with just a vacuum between the plates is C naught. And so C over C naught is going to be the dielectric constant. Okay? Meaning, like if kappa or K, if kappa has a dielectric constant of 4, that means the capacitance with it in there will be 4 times greater than when it's not in there. Okay, now why does this work? How do you get an increase in capacitance just by putting an insulator between plates? Okay, let's talk about an atom. Let's talk about an atom that's an insulator. Okay, so An atom in an insulator just means that we're using a very basic model for an atom. The protons are in the nucleus in the center, and the electrons are in the clouds, and the electron levels are in the electron clouds on the edges of the atom. And so for an insulator, these electrons are not allowed to roam around the material. They're stuck to their individual atoms. So for an insulator, electrons are not allowed to roam. If it was a metallic bond, these electrons, the outermost ones, the valence electrons, would be able to roam around. But because this is an insulator, these are stuck to here. They're not allowed to roam around. But something can happen when you put this atom into an electric field. When you put this atom into an electric field, we say it polarizes. Now what I'm going to do is watch what happens. The nucleus is going to stay put, but when I put this field in there, this electric field is going to the right. There's an electric field going to the right. We'll call that E. And what that does is it pulls the electron. Remember, electrons go the opposite way of the field. So it pulls the electron cloud to the left. Now, it's still bound to the atom, but it does pull it slightly to the left. Okay? So let's go back to here. Before you put the electric field in there, when it was just like this, the center of the positive charge is right there. The center of the positive charge is right there. The center of the negative charge is also right there. So they both have the same center. The negatives are there. The positives are both centered right there. And this is a neutral atom, okay, because we have as many protons as electrons. Okay? Again, this is a very simple view of the atom, but this gets the explanation done. Okay, when I do this, and I put this in an electric field, the electron cloud shifts a little bit, just shifts a little bit. And so now the center of the negative charge is no longer where the positive charge is. It's slightly shifted. It's like right here for the negative charge, and the positive charge is there. So we say this atom is polarized because the center of the negative charge is there, and the positive charge is there. They're no longer in the same location. So this is a polarized atom. Okay, so now what does this matter? What does this matter? Okay, so let me tell you why this affects the capacitance of a capacitor. So I'm going to come over here. Oh boy, this video is already at 7 minutes and 50 seconds, so this is going to be a little longer video. Okay, so with this, let's say we have a capacitor, a parallel plate capacitor, and this is a vacuum here. And this is the positive terminal of the battery and the negative terminal. And when you connect the battery to the capacitor, electrons from this plate zip on over to the positive terminal. And so when electrons zip on over, it was neutral, but when electrons leave, it makes this positive. And it makes these electrons come over here, and it makes this negative. Now that doesn't just keep building up charge, because what happens is the more charge that this builds up, it's just tougher to get this next electron to go onto this plate, because it's already so negative that this electron is much tougher to get over to that plate. And this electron is much harder to get to go over to this positive terminal because there's all this positive charge here. So there's a point where it reaches equilibrium, and that just happens to be doesn't just happen to be, it's exactly when the voltage across this battery is equal to the voltage across the capacitor. Okay, Kirchhoff's loop rule. Okay, so we have so much charge. You can only hold so much charge for a given voltage on this capacitor. Okay, now let's go ahead and put in an insulator to this. So we're going to put an insulator or a dielectric in between the plates. Okay, now watch what happens. When you put a dielectric into the plates, first of all, this is positive and this is negative. So this becomes positive, this plate becomes positive, and this plate becomes negative. And when it does that, it sets up an electric field in here, and the electric field is going to go from the positives to the negatives. So the electric field is going to go this way, and it's going to pull the electrons to this side. So the electrons, there's going to be a slight negative charge on these polarized atoms. So there's going to be a slight negative charge and a slight positive charge on this side. I won't do this to all of them, but you get the idea. Like this, it pulls the electron cloud slightly to this side, making this side slightly positive. We say that atom's polarized. Okay, now because of that, do you see how it's a little easier? See this electron that we were trying to get to go on this plate? Before, it was being pushed backward, repelled by these electrons. But now it's got a little bit more reason to go onto these, because look, these are all positive. And so these positive charges are pulling on that, helping you get this electron on there. So it can hold just a little more charge than it could before for the same voltage. Same thing with this electron. See these these negative charges on these polarized atoms? They're helping push this electron away from this plate, and so it's a little easier to charge this more positively. Okay, so that just helps your case for charging this. Now, yeah, so that's why when you put a dielectric in there, it's able to hold more charge. Okay, one more thing about this, and well, okay, so let's take a charged capacitor. Okay, so we're only looking at the left side right now, and this is a charged capacitor, and I'm showing you the charges here. They're set up on this side. These are positive charges. We may have hooked this up to a battery before, and these are negative charges. These little sigmas, those are lowercase sigmas. That's the charge per area. So sigma is the charge per area of plate. So the area of the plate, so that I'm making these look like they aren't three-dimensional, but these plates are actually three-dimensional. And so there's how much charge you have per area is the sigma. And so you have as much positive sigma as negative sigma. And because you have some charge on these, you get this electric field that's going across. Okay, so what happens when you put a dielectric in there is the following happens. So it's coming over here with me. Some of those lines, some of those electric field lines, they don't go all the way over to the other side. They stop at the negative charges on the polarized atoms. So what you're doing is you're taking away some of the electric field lines. And so the electric field, if this is not connected to a battery, when you put in a dielectric, if it's not connected to a battery, then the electric field goes down. Your charge stays the same, but your electric field goes down. In fact, your electric field will be the new electric field. If this is the old electric field, we'll call it capital E sub naught. The new electric field, this one right here, is going to be less, and it will be less by this much. It'll be your old electric field divided by kappa. So that's when they're not connected to the battery. Okay. One other thing about this, with a parallel plate capacitor, this is the equation for just two plates that's in a vacuum. The capacitance for only for a parallel plate capacitor is epsilon naught, which is called the permittivity of free space, times the area of one of the plates. You just use one of the areas, divided by the distance between the plates. That I took care of that in another video. Okay, but when you put in a dielectric, you change the capacitance, and so it's going to be like multiplying the whole capacitance, this, by some constant. That's the kappa constant. So so it's as though you have a new permittivity. You could not use the permittivity of free space, a vacuum, and instead use the permittivity of the material of the dielectric, and that would be the same equation. In other words, epsilon is equal to kappa epsilon naught. And I think I've already said this, but if I haven't, just to reiterate that the new capacitance will be whatever the old capacitance is times kappa. All right, so I'm in 15 minutes already, but I'm going to go ahead and try and explain the dielectric strength. Okay, dielectric strength is the electric field. So let's go back and find that chart. And the dielectric strength is, well, actually, I'm going to try and explain the dielectric strength in another, I think I'll use another video for that. Okay, hope this helped. Bye.